Welcome to ISDA 609 week 12. So we discussed linear program in week 6, chapter 7 of the textbook. And for integer program, we have a supplemental text, chapter A. And for nonlinear program, it will be chapter 13. So this chapter is actually covering the nonlinear program. So we talked about this inventory problem earlier in the textbook, and the total cost is a minimize of the cost of delivery and storage cost. So assume that this is a delivery cost and this is the storage cost, and then this is the total cost. How can we find the minimum point, i.e. the optimal between the cycle and cost, so that we can minimize the cost. And when we have suppose the maximum R revenue, and we have different P1 times X1 as a revenue and P2 times X2 as the revenue for P2. So in this case, because if we have x1 times this p1, it would be x1 times x1, meaning x1 squared, and also we have a term of x1 times x2. Now the function becomes nonlinear. And then we can use first order derivatives to solve the problem, partial derivatives, and set them to 0 and solve x1 and x2. And we use second order derivative to confirm it is indeed a maximum because it is less than 0, so that we can consider the curve would look like this, and then there's a maximum value there. And another method is a gradient method of the steepest ascent. So we take the partial order derivative, find lambda k, so that we can move based on the steepest ascent direction. Nonlinear least squares, similar to the linear least squares method, using the observed value minus the model value, so that we can get the sum of squared error. And we can take partial derivatives on both parameters and solve for a and b. And here, constraint continuous optimization. This example is minimize this, and there's a constraint. And then we can model this, use a Lagrange multiplier using the objective function plus lambda times the transformation of the constraint, which is this minus 24. So this is the function. Again, we can take partial derivatives and set them to 0, and we can solve for lambda and x1 and x2. And this is the objective value, which is 12.71 for this particular case. This is another example to use Lagrangian method. So very similar here. This is the lambda as a Lagrangian multiplier. Partial derivative, and solve for h1, h2, and lambda. Find the approximate total surface, the volume. This is another example how to manage renewable resources. and first order derivative again. Homework for chapter 13. Thank you.